Hi, welcome to Digital Dialogs, your compact conversations on the future of technology. My name is Renee from Reply, and today we're going to talk about unleashing contextual understanding in robotics with open vocabulary scene graph. What a title, isn't it? And as much as it sounds like rocket science, it's kind of rocket science, but we have a true expert here today that will tell us all about this. Federico Minutoli. Ciao Federico, come stai?
So, Renee, thank you. It's great to be here. Doing good. Ready for it.
Awesome. Well, Federico, can you tell us first a little bit about yourself and your background as it relates to, anything researchy, robotics, or, AI, data science, whatever? Like, tell us a little bit about yourself.
Yeah, for sure. So, I graduated in computer engineering and computer science a while back, and I've always been fascinated by computer vision, natural language, and multi-agent systems. And these fields have a very nice intersection in robotics and semantic perception, which is basically what I've worked on for quite some time now, and especially what I've been doing at our innovation laboratory at Federico in Italy. And in that field, there's a lot going on at the moment between extremely fast vision systems, between large natural language models, and the way we want to understand and perceive reality. So I'm very keen to be working on this. And I'm also involved in a lot of open source projects, sharing, collaborating with the community to push the boundaries even further.
Woohoo, open source for the win. I'm always a big fan of that, and I'm glad to hear that you're also very much involved in that. So, Federico, let's talk about some of the open vocabulary. First of all, can you explain what is open vocabulary scene graphs and how these algorithms enable robots to, in the end, better perceive and navigate dynamically changing environments, right? So, explain what this is, what is ongoing, and please also what is some recent research and techniques that are currently evolving in this field.
Yeah, so I would start from what open vocabulary means in the first place. And that basically means that instead of having a fixed vocabulary or a classifier, we are trying to mimic how humans perceive and elaborate language. So we have a very large vocabulary. We don't need to be trained on a small subset of labels or tags. And that's the kind of goal that we have there. We want systems to be flexible, to being able to understand nuances in the language and being able to refer to the same object in different ways. Think table or desk in different contexts, or capability like grasping, grabbing, picking. They all kind of resemble the same meaning, and we want to have that sort of flexibility in our systems. So open vocabulary maps of the environment are crucial to accomplish tasks in the real world.
Mm-hmm.
And this is because we express in natural language and we are often ambiguous. So when we create a semantic map of the environment, we try to disambiguate objects and the scene for robotic agents to then accurately achieve their desired goals. And the concept of 3D scene graphs had been introduced in 2019 by Armin et al. At Stanford. And as of now, it seems to be the most effective data structure for these applications. 3D SGs are very useful because they map the spatial structure of environments in a way that very closely mimic our perception by creating hierarchical representations of environments, starting from buildings into floors, into rooms, into specific objects inside them, as well as functional relationships between elements. And we'll see an example later. So this is a structure which scales very nicely to large-scale environments, unlike some other advancements in the field, like 3D volumetric reconstructions, unlike dense neural radiance fields. And, and so it's very useful if you want to have a lot of agents, think of a fleet of agents working on a very large environment.
Mm-hmm.
They're also useful because they allow storing extra information, heterogeneous information like properties, metadata, both at the node and the edge level. So this reaches a lot the amount of data that we can add, and this all enhances the robot's ability to plan and execute tasks. So to give an example, think
Yeah.
of a known robot with manipulation skills. It might utilize a 3DSG in the house that might be representing a kitchen, and the kitchen be containing a refrigerator, which in turn stores food items. And it might have spatial relationships, like the chair is underneath the table, but also functional relationships, like the refrigerator handle gives way and access to the food. So these are all little semantic elements that put together allow agents and planners to actually execute complex tasks in environments.
Gotcha. That is a beautiful explanation. So, like you're saying, that's also very much like how we humans think about our world in a sense of a hierarchy, that these object or I mean, there's also on the philosophical standpoint, there's also like how our universe is built with there's this called aggregation theory, which is quite interesting. But in the end, it's like it is, right? Our world is an aggregation of smaller objects that become bigger objects, and so you have this hierarchy there, and adding the semantics to these objects, like you're saying, is obviously a much better than having to deal with a huge neural radiance field in the end, a huge point cloud, and having all these little details. You rather need a broader semantic understanding of it, and that is pretty cool. So, what are some of the recent research or algorithms in that field that you can share?
Yeah, for sure. What Luca Carlone and his team at Professor Luca Carlone and his team at MIT have done over the past few years has been nothing short of amazing, like truly tremendous stuff, starting from Chimera for metric semantic reconstruction into then Hydra and Hydra Multi for 3DSG reconstruction. And Hydra Multi is even more amazing because it allows a fleet of different robots located in different areas of the environment to actually share the information they gather and co-build a globally consistent 3D scene graph. But we are now also seeing a lot of research and efforts going into automatically building these sorts of graphs using large language models, using visual language models. And we've had an example in concept graphs, which is a very interesting experiment of putting together open vocabulary semantic segmentation models with large language models and visual language models. And we have worked a lot with that. But we'll talk about it in a minute because there's good and there's bad, right, with everything. The more you want to add to the graph, the slower it becomes, the larger it becomes. So there's also a lot of infrastructure talk that we have to go through because the path to actually put together this novelty research into the real world, into real world systems, is actually to solve not only the algorithmic part but also the infrastructure part. But these techniques have brought a lot of advancements, and now we have the very first examples of scene graphs being built in real time around the robotic agent and being able to not only reconstruct the overall structure of the environment but also understand details about individual objects.
Makes sense. Makes a lot of sense. So let's talk about the challenges at the end a little bit more, and the future prospects there. But what I was also interested in, since we're a little bit focusing on this season of the podcast on the humanoid robotics aspects, what do you see in terms of improvements that are possible for a human robot interaction, especially in unpredictable scenarios?
Yeah, that's a great question and a key aspect because a lot of the robotics world right now is focusing on humanoid robots, as you know very well. And they are maybe the robotic form factor that we want the most to behave like humans, and so they have to understand the most how
Yeah.
us as humans express ourselves. So I, I would say that it's especially important for such robots that might be operating 24/7 to be robust in unpredictable scenarios because they have to follow instruction precisely in order to avoid damage or failure, right? So if we ask them like, bring me the mug from the kitchen or something, we want them to explore the environment very, very nicely and identify the kitchen area, locate the surface the mug might be on, such as the counter, it might not be fixed, and then distinguish the mug from even other objects. So it needs also low-level skills, while planning to avoid maybe fragile objects like vases. We never would want our grandma's flower vase on the floor being broken into pieces. So having this graph structure allows the inclusion of formal planning algorithms from control theory that not only verify traversability of the environment according to the robot specifications, because a drone is very, very different from a human robot, which is very, very different from a wheeled robot or even from a quadruped, but also they validate the soundness of the plan. And this enables the robot to execute the task more reliably, but also we can even add structural graph leaf algorithms that enable real-time structural verification of the graph. And so if we have stored 3DSG in the past, so we have a memory of what the graph looked like, and then the robot gets into that specific scene and he has a fast enough local reconstruction algorithm, we can easily compare the two and derive insights in the underlying global structure if there were any changes. And this allows the robot to analyze if something is off, if something has changed, or in general to cope with the dynamic elements of the scene. And this is very important to handle such scenarios.
Yeah, that makes a lot of sense actually. Um, let's talk about the challenges and opportunities that you would also see in the future, because that's, I think, also interesting when we think about integrating these systems into robotic platforms. Like you already alluded a little bit to it, what are some of the challenges? But what challenges you face actually integrating these robotic platforms, and what advancements in the future do you see that might help to solve those?
Yeah, for sure. So integrating such systems into robotic platforms still presents several challenges, as I was saying before. And the OpenVOC capability, for starters, is constrained by the expressiveness power of these underlying large models. They can be embedding models, they can be large language models, but they basically put a cap on how much we can understand of the world. So they're little world models that we are using to understand and perceive
Hmm.
what's around us, right? And yes, fine tuning and prompt engineering can yield some improvements, but the majority of this reasoning stems from common sense knowledge, which is in the model's backbone and emerged from training on internet petabyte scale data. So mistakes or inaccuracies at this level are detrimental to the pipeline because they carry over to the whole pipeline. And if, I don't know, we detect a little TV remote as whatever other object, and the model, of course, would not know where that is located, how to reason about a specific object, and that falls apart the whole pipeline going forward. So there's a very, very important challenge in grounding high-level actions into low-level capabilities to mitigate potential errors in the perception of the environment around us, which is very, very good at the moment, has improved a lot, but it's not quite there. And this requires a very precise controller to create a mapping, right, between abstract instructions, high-level instructions in natural language,
Hmm.
and then the concrete actions that the robot has to do to actually carry it out. And then there's also another challenge, which is in the construction of the graph itself, because most of the literature and research world in academia is focusing a lot on environments and benchmarks, which are often static, because that's an easier setup to work with. It allows you to iterate faster and have a more grounded comparison between different algorithms, advances, etc. So you put yourself in the same conditions over and over, so you typically keep a static scene. But dynamic graphs that are able to distinguish between still and dynamic elements and gradually add it in real time are actually what's needed for deployment in real environments where things change quite fast, especially in most indoor scenarios where we might see these kind of robots to operate.
Yeah.
And at the moment, there's a trade-off between the generation speed of the graph and the content richness. So even if we think about the Hydra system that I was mentioning earlier, right? It's very good it runs very, very fast in real time. But there's a catch. At the moment, it only attributes labels or tags to objects. You cannot go deeper. You cannot try to extract even richer descriptors that kind of describes these objects. And this is something that we have experienced firsthand ourselves in Air42, because we have experimented a lot, not only with different models, so with different open source models, flagship models, etc., but also in how much we wanted to push the richness of these semantic descriptors. Yeah. If we could extract even affordances, how you want to interact with that specific object. And at the moment, there is so much we can ask for in models and infrastructure. And there's a very, very clear trade-off if we want to keep reconstruction latency affordable, manageable, and very, very close to real time. But I'm also very excited. And I'll tell you why. Because future directions in this field align very closely with current trends in AI and generative AI, especially both at the models and infrastructure level. Think about graph storage and querying. Like GraphRug from Microsoft has shifted a lot of the industry's attention towards building more reliable, efficient, scalable graph stores and graph query engines with better integration with LLMs. And at the same time, fine-tuning and running inference for LLMs and VLMs has never been easier.
Yeah.
And moreover, the neurosymbolic AI community's work, like in combining LLMs with formal rules, trying to build more efficient planning and problem solving in complex environments, has already shown great results. And I don't foresee any of that slowing down anytime soon. And all these little pieces are actually what's needed to build a 3D scene graph very, very efficiently, very, very fast, and then being able to query it at a fraction of the time, at a fraction of the cost, deploy it in a real-world environment so that the robot use it to better understand and interact with increasingly sophisticated environments. So there's a lot to be excited for in this
field. Yeah, and definitely exciting things are happening, and also, like you're saying, is like with the advantage of language models and transformer architecture, a lot of things fall together and are being accelerated as well by this, right? But there's also this other camp like Jan LeCun with objective-driven AI that is actually also proposing, like I said, this objective-driven AI with joint embeddings and so on, where you build this world model and you also have this hierarchy in there, right? So it kind of sounds also a lot what you were describing today in these open vocabulary methods, what I hear there. So maybe that the way is to have like kind of a hybrid where you combine these various aspects, so that you combine this kind of world model and these hierarchies with a large language model or something like this. I don't know. What are your thoughts on that?
Yeah, I think that's a probable path forward, like having hierarchies of different models at different levels that do different things, and everything is brought together from a very, very fast engine that is able to perceive the locality of the world, to having slower engines that actually have world knowledge and common sense knowledge behind it, and it all falls together into a single piece that then allows us and these models to perceive reality, perceive what's around us, being grounded in the form factor, because again, a drone has to act very, very differently from a human robot, and at that point operate in environment. So there's definitely a path forward there.
Gotcha. Makes a lot of sense. Well, Federico, we're unfortunately already at the end of our time today. We could talk for much, much longer. That was a fantastic conversation, and I really enjoyed hearing all the insights into these, open vocabulary worlds, basically. Well, thank you so much, Federico, for joining us today and sharing your knowledge. Very much appreciated.
Thank you, Renee. It was a pleasure to be here. Thank you for having me.
Well, and thanks everyone for joining us for Digital Dialogues, your compact conversations on the future of tech. As usual, you know what I'm saying. Watch our blog, follow our social media channels, and of course, subscribe to the Reply Talks podcast channel on all the podcast platforms. You name them, right? Spotify, Google, Apple, Amazon. I'm sure I forgot a few, but we're all on all these podcast platforms. So just make sure to subscribe there. And of course, you can also always go to reply.com to find all the previous episodes and also the upcoming ones. So make sure to check this out as well. Until then, folks, take care and see you soon. Bye bye.